Today we're going to derive and learn about a new tool that we have for problem solving called the Work-Kinetic Energy Theorem. So if we start with Newton's second law, net force equals ma, and also then use the time-independent equation of kinematics, and then we solve for acceleration and substitute. So acceleration would be net force over m, plugging that in gives us 2 times net force over m delta x equals v final squared minus v naught squared. And then rearrange net force times delta x is equal to 1/2, moving the 2 over, multiplying by mass, and then distributing gives us this. Net force times delta x equals 1/2 mv final squared minus 1/2 mv naught squared. So this is the work-kinetic energy theorem. This on the left side over here, if the force is constant, then this is equal to the work done by the net force. And so we can say work done by the net force is 1/2 mv final squared minus 1/2 mv naught squared. 1/2 mv squared is an important quantity that you may know about already. Is called kinetic energy, or energy of motion. We will represent this with the variable k. So another way of writing this work kinetic energy theorem is just the work done by the net force is equal to a change in kinetic energy. And depending on the situation, we might plug in force times distance over here, or we might plug in the integral definition of work. And on the right side, we'll probably most of the time plug in this formula, although if you're given values for kinetic energy or asked to find a value for kinetic energy, you might just leave it as kinetic energy final minus kinetic energy initial. And of course, we know kinetic energy is 1/2 mv squared. So it depends on both mass and velocity. It depends more on velocity. So, an object that has half the mass and twice the velocity would have double the kinetic energy because the mass there's a linear relationship between kinetic energy and mass, but the quadratic relationship between kinetic energy and velocity. So if you double the mass without changing the velocity, you double the kinetic energy. If you double the velocity without changing the mass, you quadruple the kinetic energy, and so forth. So this is a tool that we can use to solve problems. For example, 1,200 kilogram car slows down from 17 meters per second to 12 meters per second. We want to know how much work is done. Well, we know work done by the net force is equal to change in kinetic energy. Depending on what you're solving for, it can sometimes be useful to factor this equation, rewrite it like this. And in this case, we have the values we need to plug and chug away. Conceptually, you'll notice that anytime the speed of an object decreases, that means that negative work is being done on the object. Anytime the speed increases, that means that positive work is being done on the object. If the speed stays the same, then the work done is 0. So the work done in this case is minus 87,000 joules. We can combine work-kinetic energy theorem with anything we've done previously involving work. So if we see this force, it begins at rest. What's the speed when it's traveled? 4 meters. Well, we know work done by the net force is equal to 1/2 mv final squared minus 1/2 mv naught squared. We know that this mass starts from rest, so v naught is 0. And in this case, when you're given a graph, to find the work, we can find the area under the curve. So do that real quick. Rectangle 1/2 is just an area of 2. This trapezoid, we've got base 1 is 2, base 2 is 4. Add this together, get 6. Half that's 3 times 1. It's an area of 3. And this is 1/1, so that's 1. So the work done by the net force is 3 plus 2 minus 1, and then we set that equal to 1/2 times 5 times v final squared, and then we can solve. That's 8 over 5, square root of 8 over 5. That's a lovely number. So the final velocity is about 1.26 meters per second. The speed. Yeah. Continuing on, here's another example. Boat's motor does 65,000 joules of work on a 130 kilogram boat. As it goes from rest to 24 meters per second, how much work does the resistive force of the water do? I should have stated the assumption that these are the only two forces doing work. So work net is equal to, change in kinetic energy, 1/2 m v final squared minus 1/2 m v naught squared. And the work done by the net force is equal to the sum of the work done by all the other forces. So in this case, we're given work done by the force the motor generates, 65,000 joules, and then that combined with the work done by the resistive force of the water. Sorry, I started to write F. Work done by the resistive force of the water is then equal to 1/2 m. Starts from rest, so V naught is 0. And then we can go ahead and calculate. And the work done by the resistive force of the water comes out to minus 27,560. We stop and think for a moment. Does that make sense? Well, the resistive force would be acting in the direction opposite that the boat is moving, so it does make sense that that would do negative work. Consider number 14 here. We've got a 2 kilogram ball attached to a string, moving in a horizontal circle at constant speed. How much work is done on the ball in each revolution? Well, we know work is equal to change in kinetic energy. Well, if the speed is constant, then the change in kinetic energy is 0. So the work done by the net force is 0 joules. And you could figure that out conceptually because the force that's causing this to move in a circle points toward the center of the circle. So that force is always perpendicular to the velocity. And when force and displacement and a small bit of displacement would be perpendicular, that means that there's no work being done. We know that from the basic definition of work.